In this series, we're going to take a closer look at Bessey sequences and some of the shuffles that preserve or invert these sequences. So as the foundational definition, we have the following. A shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall the Bessey sequences of order 8 are the following: 1 0 0 1 0 1 1 0, and its inversion 0 1 1 0 1 0 0 1. Those are the only two Bessey sequences of order 8, and we say that they are the inversion of one another. Informally, you can just think of them as resulting from the other by switching zeros for ones and ones for zeros. To anchor the labeling of the positions of the elements of these sequences, I've listed 1 through 8, and then below those numbers I've indicated either a 1 or a 0. So for Bessey sequences of order 8, there are only two possibilities. First one, the ones are in positions 1, 4, 6, and 7, and the zeros are in positions 2, 3, 5, 8. Or if we consider the inversion of this Bessey sequence, we get the following. The ones are now in positions 2, 3, 5, 8, and the zeros are in positions 1, 4, 6, 7. To further aid us in understanding the diagrams on the left-hand side of the screen, I've color-coded the different digits. So if you want to picture these as a black card, a red card, a red card, black, red, black, black, red, that would work just fine as a model to represent the structure of a Bessey sequence. And here I've identified a set A as consisting of the positions 1, 4, 6, 7, and its complement, that's what the bar means, the complement of A, consisting of the positions 2, 3, 5, 8. Now what this means here, and it's also found on the top left-hand side of the screen here, so like if you can see the hand moving on the left, in each corner I have a little diagram. So this first one, what it's denoting is the objects in these positions, 1, 4, 6, 7, after they've been rearranged or shuffled, will still be in positions 1, 4, 6, 7, even though they may have traded places within these four position values. The same thing here. This depiction represents the objects in position 2, 3, 5, 8 as staying in those positions, 2, 3, 5, 8, even though they may switch places within this list of position values. Now that's in contrast to the following, where we have the objects in these position values. After the shuffle, they get moved to the positions that are found in a complement, namely 2, 3, 5, 8. So in other words, there's a wholesale exchange of the 1, 4, 6, 7 with some assignment of 2, 3, 5, 8. It's like they just switch places. For example, if the reds and blacks all switch places here, that would mean that in the first position it would now be a red card, namely one of the ones that initially started out in position 2, 3, 5, 8. The next one would be black, and then black, red, red, black. Okay? This will become clearer as we move ahead. Okay, so let's go a bit more deeply into the mathematics. So if you focus here on the left, we're going to look at what is called the LR shuffle. That's shuffling into a left and right pile, in which we will stack the left pile on top of the right. And it leads to this permutation. Okay, so we're going to talk about permutations and notation for permutations. Okay, and I promise you this is not that difficult. Anyone can follow this, regardless of your mathematical background. Okay, so to figure out what permutation is associated with this shuffle, what we do is we begin with cards clearly labeled 1 through 8. These numerals are really just marking the original position of these cards. That's the whole reason for the numerals. Okay, so that's where we're starting. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now what you do to find the permutation associated with that shuffle is you turn the cards over and you perform the shuffle. So we're going to do a left-right with stacking left pile on top of the right. Very good. That is the shuffle. What is the new ordering brought about because of that shuffle? Well, let's take a look. Okay, let me just put this down so you can see it. So it's 7, 5, 3, 1, 8, 6, 4, 2. Okay, so what I've done here is I've simply written down the new ordering. 7, 5, 3, 1, 8, 6, 4, 2. And this is called Cauchy's two-line notation. It's a way of representing permutations. It's a way of representing the result of this shuffle on this packet of 8 cards. Now this isn't what we have up here. We have something far more compact. So what we do is we change this two-line notation into something called cycle notation, or in other words, one-line notation. So this is far more compressed and succinct. Okay, so the way that you get the one-line notation, so the way that I got the 1, 7, 4 up here, so you just read it off here. So we see that 1, so what was in position 1 gets replaced by what was in position 7, right? So 1 goes to 7. So we say 1 goes to 7. Where does 7 go? 7 over here, we're looking at the top row. 7 goes to 4. Very good. Where does 4 go? Well, 4 goes to 1. Well, guess what? That wraps around. We started at 1. We went from 1 to 7, 7 to 4, 4 to 1. So that creates a little cycle of 3 elements. Okay? So a way to compress all of that information into as few characters as possible is the following. We start with an open left parenthesis, and then we just write the value 1, 7, 4, and then close with a right parenthesis. Where the assumption here is the 4 wraps around to the first value in that cycle, namely 1. So the information here is capturing what's happening with 3 of the elements in our original sequence. Okay, now let's take a look at some more here. So 2 goes to 5, so there's an arrow there. Where does 5 go? 5 goes to 8, so I've written an 8 to the right. Where does 8 go? 8 goes to 2, and 2 is where we started, so it wraps around. So all of this information here can be consolidated into just these symbols here. Parenthesis, 2, 5, 8, close parenthesis. Okay? Now what is happening with the others? So look at 3. Ooh, that's interesting, and you can see it. So remember, this is the top card. So this is position 1, 2, 3. Oh, the card in position 3 stayed in position 3. So that's why we have an arrow from 3 to 3, and we write it as a single cycle. It's called a fixed point. So if you perform this shuffle 1 time or 1,000,000 times, 3 stays right where it started. It doesn't go anywhere. It's a fixed point. The same thing happens with whatever was originally in position 6. This is position 6. It didn't go anywhere. It stayed right where it is. Despite all the movement of those cards, as we're shuffling it, the cards in position 3 and 6 just arrive back where they started. They did not get moved to a new position in the end. Now, ordinarily, these one cycles, we call them, are not necessarily included in the cycle representation of the permutation, provided that the context is clear regarding the size of the set you're working with. So as long as we're clear on the fact that we're looking at 8 objects, we can safely drop these. And because a 3 is not present, it's assumed to be a fixed point, which it is. And because a 6 is not present anywhere in these parentheses, it's assumed to be a fixed point, which it is. Now, if we color code these, which gets us closer to reading the diagrams on the left, the cycle notation for this permutation would look like this. Remember, 1, 4, 6, 7, we color coded them black. 2, 3, 5, 8 are color coded red from earlier. And I've included the single cycles just so that we can see the following. Each value gets sent to a value of the same color, because 1 gets sent to 7, both of those are, quote, black. 7 gets sent to 4, which is black. 4 gets sent back to 1, which is black. Same thing here for 2, 5, 8. And over here, 3 gets sent to 3, which is red. Starts out red, ends red. Same thing here for 6. It's black. Starts out black and ends black, because it's being assigned to itself. So what I thought we would do is go ahead and draw by hand the first Bessey Shuffle diagram on the top left, up over here. We'll do just one of these by hand, just so you can see how it's constructed. Okay, so for this shuffle, the left-right shuffle, on which we stack the left pile on top of the right, as just illustrated, leads to the following permutation. So 1 gets sent to 7. Okay, so what you do here is you start at 1, 1's right there, and you draw an arrow for 1 to 7. That's all you do. So I'll just draw an arrow from 1 to 7. And the direction is as follows. We're going from 1 to 7. Okay, so 1 to 7, 7 to 4. Okay, so 7 goes to 4. And in just a moment, I'll give you some additional ways of interpreting this 7 goes to 4. What does that really mean? Okay, so we'll give you some practical ways to make sense of that statement. Now, going back to our cycle notation, 4 wraps around and gets sent to 1. So that means we just draw a line straight up. And it would go with an arrow pointing upward, because it's 4 goes to 1. Okay? So now we have to look at the second term in our permutation. So 2, 5, 8. Okay, so 2 gets sent to 5. So I'll draw a line, a directed line, an arrow, from 2 to 5. Just like that. And then 5 goes to 8. Okay, so it just goes straight up from 5 to 8. Just like this. Okay, and then 8 wraps around and goes to 2. So 8 goes to 2. Okay, so we draw a line from 8 to 2 with an arrow pointing towards 2. Okay, and then something else interesting happens. Because 3 is not present, and we already know that it's a fixed point, what that means then is you can just draw it with no markings at all as far as an arrow, which is what's done on the computer drawn version up there. You can also do this, which is just fine, where it's indicating that 3 is sent to 3. 6 is sent to 6. So they don't move anywhere. They're fixed points. And then let's take a look at what's happening with set A. Remember, the set A consists of the values 1, 4, 6, 7. Well, what's found in positions 1, 4, 6, 7 either stay where they are in the case of 6, or they get assigned to one of the other values in that set, 1, 4, 6, 7. So we would say that A gets sent to A. Well, once we know that, then we also know that A complement, which are the red vertices there, red points, so 2, 5, 8, and 3, those get sent somewhere to themselves. Either they're fixed, as in the case of 3, or they just get moved around, permuted among themselves, at 2, 5, 8. So in this case, we would say that this shuffle preserves Bessey sequences of order 8. Okay, now in a minute we're going to do another shuffle where it inverts it. It sends A to A complement and A complement to A. Now that will pose no difficulties for us moving forward. That is perfectly acceptable for that to happen. It will not undermine anything we hope to do. So I thought I would give you kind of a metaphor or narrative to make sense of the colored dots on our diagram and the arrows pointing in certain directions. So what I want you to do is picture, if you've seen Monty Python's spoof involving I think it's maybe a 100-meter dash, where you have these ancient figures, Archimedes and Karl Marx and other philosophers running, seeing who can run the fastest. Okay, so it's just a silly little Monty Python spoof. Okay, so these are their starting positions. So this guy here, William the First, starts in the first position. Edward Elder in the second, and then we have third, fourth, fifth, sixth, and then all the way to Ethelred in the 8th position. Okay, so what we want to do is we're going to have them run this 100-meter dash, and then we'll see how each of them did at the end. Now the way that we'll get the new ordering for these runners is we'll just perform this shuffle that we've just done. The LR with left stacked on right. Okay, so I'll do left, right, left, right, left, right, left, right, stack left on right. Okay, that's the shuffle we've been doing. Okay, now we know what order is going to come out because we've seen it already, right? So we're going to get, of course, 7 will be first, then 5, 3, ace or 1, 8, 6, 4, and then a 2. Okay, so that agrees with what we did earlier. Now the way to think about these is when we're looking at the diagram here that we've just drawn, is think about it in this way. First, so the race has been completed. Okay, they've run, and this is this is the first person to cross the finish line, second, third, all the way up to the last person, the loser over here, last person to cross the finish line. Okay, so what does this mean? This means that first place goes to the individual who was originally in 7th place, right? Because we had them ace through 8 originally. 7th place, over here, this is 7th place, goes to whoever was originally in the 4th position. And that's what we see here. 4th place, which is over here, goes to the individual who was originally in position 1. And that is the person, William I, was originally in position 1. Okay? So this is a way of interpreting really what's going on. So we say first place goes to whoever started in the 7th position. So the arrow going from 1 to 7 is best interpreted in that sort of way. So first place, so the new first position, first place goes to whoever started in the 7th position. And second place goes to whoever started in the 5th position. So is that true? Second place goes to the person who originally started in the 5th position. That's true. We see it right here. The second place winner is now the 5 of hearts, and that 5 of hearts started in the 5th position. Okay, so you can think of these as assigning a new placement order to the cards after the shuffle has been completed. And we can read it from here. So first place goes to 7, the card that was in position 7. 7th place goes to the card that was in position 4. 4th place goes to the card that was in position 1. Second place goes to the card that was originally in position 5. 5th place, right here, goes to the person who was originally in position 8. And 8th place over here goes to the person who was originally in the 2nd position. Okay, so that's a way to interpret these permutations written in cycle notation or as a shuffle diagram, as depicted here. So I'm hoping that explains how it is I got this diagram here on the left for the permutation that results from performing this particular shuffle. And as some specialized vocabulary, we say that 2, 5, 8 are in the same orbit. So that's a technical word from group theory. So one orbit is the set consisting of 2, 5, 8. Okay, oops, sorry about that. So that's one orbit. I'll say orbits. Another orbit is one consisting of just 3 because it doesn't go anywhere. And then 2 other orbits, I'll go ahead and just do them in black because we have them color-coded in black, will be 1, 7, 4. So it's like they just cycle around. They just trade places sequentially there. So 1, 4, 7. I've just listed them in order, which doesn't matter when you're writing set notation. And then the remaining orbit is the one over here for 6. 6 is in its own little orbit, since this shuffle leaves 6 alone. And the important thing to understand regarding Bessey sequences is that all of the red values after the shuffle will stay within positions marked by the red values, and the same thing for the black values here. After the shuffle, they'll stay in positions that are marked black, namely 1, 4, 6, 7. Okay? If you've watched the Bessey sequence videos on this playlist, you'll know that these are the 2 Bessey sequences of order 8. So 1, 0, 0, 1, 0, 1, 1, 0. Okay? So what I thought we would do, this is just meant to kind of reinforce what's going on so that you can develop some real intuition for the inner workings of all of this. Okay? So the claim is this shuffle that we have just shown you, namely this one right here, the LR shuffle where we stack left on right, it ends up preserving the Bessey sequence. So if we start with this version of a Bessey sequence, 1, 0, 0, 1, 0, 1, 1, 0, the claim is if we perform the LR shuffle with left on right, we will get that exact form back. Okay, so it won't invert it, it will actually preserve that form. Okay, so what will that mean? That means we get back to 1, 0, 0, 1, 0, 1, 1, 0. Okay, and as you might imagine, if we were to reverse this and start with the inversion to begin with, we're going to get this back if we perform this particular shuffle. Okay, so it truly does preserve this structure type here. Okay, so if it was originally of a Bessey sequence of this arrangement, it's left that way, or if it started out in this configuration, then it would end in that configuration. Now, it is true that, quote, under the hood, this is really, really important. It is true, well, why don't we go back to the original one. But I do want to point out something important here. Because I have 1s on 4 of these and 0s on 4 of these, and we're assuming that those are indistinguishable. The one, any one of the ones is indistinguishable from the other ones, and same thing for zeros, which is technically not true because they're of different size. Like this is a huge zero. But assuming they look exactly the same, shuffling this doesn't mean that we arrive back at the exact original ordering of the cards, because we don't. We saw what we get back. It's not that, right? It's this. This is the new ordering, okay? But it just happens to be the case that cards in position 1, 4, 6, 7 are all ones. Cards in position 2, 3, 5, 8 are all zeros. So we don't detect that anything has changed. Well, technically, the ones have been moved around among themselves, except for the 6th position, 1. And the zeros have been moved around among themselves, except for the 3rd position, 0, right? Because we know that the 3rd position card is a fixed point, right? It doesn't change, okay? So I thought I would relate it to the zeros and ones that we've been studying in most of the other videos on this playlist, okay? So that's kind of relates what we've been doing to what we're doing now. So to quickly give a fun little application of all of this, so I have this arrangement of the kings and queens, and really anyone looking at this would almost certainly not see anything of consequence. They wouldn't look at that and go, oh, that has a special structure to it. It doesn't seem to have anything to it. Now, you knowing what Bessey sequences are, just taking a moment or two, you'll recognize that this is a Bessey sequence relative to kings and queens. Well, that being the case means that we can perform the shuffle that we've just been using, the left-right, with stacking left on right to this packet of cards, and it will return it to its original structure type. Okay, so here we are. We're back to a queen on top, which is what we had at the beginning, and then a couple of kings, then a queen. Okay, so this is like 1, 0, 0, 1, and then 0, 1, 1, 0. Okay, so how would that help us? Okay, well, if you just hold the cards face down, we know for one thing that the top card is a queen. Okay, so what we know then is there's a queen, a king, king, queen, king, queen, queen, king, okay? Just because of the assignments. So that means I know that this is a queen, the next two are kings, this one's a queen, this one's a king, the next two are queens, the last one's a king, okay? And so I could have performed that left-right shuffle with left on right. I could have done one of those or 5,000 of those, whatever the spectator asked for. And then after doing all of that, I could separate these 8 cards into 2 piles, one consisting of the queens and one consisting of the kings. Moreover, I would know which is which. And isn't that amazing? So I could say, well, we did all that mixing. Let's say we did that shuffle 7 times, and that's what the spectator asked for. And then I did this, 1, 0, 0, 1, 0, 1, 1, 0. To deal them down, to separate the queens from the kings. And then I could come over here and say, wow, as I was dealing those down kind of in a random fashion, it just felt like certain cards should go left or right. And that's all I did. I just kind of felt just a little push in a certain direction to put each card on the left or on the right. Okay, and I think I put 4 cards in each. I wonder what I put in each one of these. Well, that's weird. These feel like they're all the same. There's no way. These are all the same value? Well, if they are they kings or queens? Ooh, I think, these are the queens. I can just tell. Queens have a different aura and resonance than kings do. I think these are the 4 queens. What are the chances that I just happen to separate all of the queens into one pile? Oh, I can't believe it. I just put them down left, right, according to just little subtle impressions I had as I was dealing those. Isn't that amazing? I wonder if I could do that again. And of course, you can do it as many times as you like, forever. because of the mathematics, right? Okay, so anyway, that's just kind of a simple example of how you could use what we've shown you thus far. Okay, so let's take a look at these other permutations. Okay, so the next one's different. So why is it different? Well, it's because inversion happens. Okay, so we're looking at the one on the top right, but still on the left. This one over here. Well, what's different about this one? We're stacking right on left. That's the only difference. Even though I said we would just do one of these by hand, why don't we do at least a portion of this derivation? I'm beginning with the cards 1 through 8, and I'm going to perform this shuffle permutation, namely a left-right, but this time we'll stack right on left. Okay? So that's going to change things. In fact, in what way does it change things? Well, you get an 8 first. Oh, I'm sorry, going off the screen. You get an 8 first, 6, 4, 2, 7, 5, 3, 1. Okay, so this is the new ordering. So I can go down here. So 8, 6, 4, 2, 7, 5, 3, 1. Well, how did we change this to one-line notation? In other words, cycle notation. Well, what we do here is you just read it off. 1 goes to 8, 1 goes to 8, 8 goes to 1, so it wraps around. So that's we call it a transposition. That's a 2-cycle. That's a 2-cycle with a small c for cycle, by the way. Okay, and now for 2 goes to 6, 6 goes to 5, 5 goes to 7, 7 goes to 3, 3 goes to 4, 4 goes to 2, which wraps around. Okay, so look at that. We only have 2 terms in our permutation here. We have a transposition. A transposition just means those 2 elements get switched. That's all it means. And then these others, there's quite a bit more going on. Okay, but look at what happens now with the color coding. This is very, very important. Remember, 1, 4, 6, 7. We associate that with the black color coding. And then 2, 3, 5, 8. We associate that with the red color coding. Okay, so 1 going to 8 and 8 going to 1 would look like this. So we have a black value being sent to a red value, and a red value being sent to a black value. What happens over here? We get the red value 2 being sent to a black value 6, being sent to a red value 5, being sent to a black value 7, being sent to a red value 3, being sent to a black value 4, being sent to a red value 2. Okay, very curious. So what's happening here is each of the numbers 1, 4, 6, 7 is being sent to one of the numbers 2, 3, 5, 8. So it goes back to what I mentioned about the sets switching places. It's like the sets just switch places. Okay, so what's happening here is all of these values get sent to those new positions, and these values get sent to those new positions. Okay, so there's an inversion going on here. It kind of inverts everything. Okay, and so that's what I have down here. Each value gets sent to a value of the opposite color. Okay, and so that is why I have, if you look at the top left here in the middle, look at this. Black A, so A gets sent to A complement, and A complement gets sent to A. So this is a true inversion. Okay, so in the language of zeros and ones, we can actually quickly demonstrate that. So if we begin with this particular Bessey sequence, 1, 0, 0, 1, 0, 1, 1, 0, and we're going to go ahead and perform this shuffle permutation, left, right, with stacking of right on left. The claim is that now we will get a 0, 1, 1, 0, 1, 0, 0, 1. So it sent the original Bessey sequence to its inversion, or it inverted it. Okay, so that happened here, but it did not happen with the first example, right? The first example, we stayed within the same color values, if you want to think about it in that way. Okay, And look at the diagram for this one. This is a really fun shuffle diagram here. So look at the diagram here. Very interesting shape there. Very different than this one. Okay, so would you be able to draw this? Well, see, 1 goes to 8 and 8 goes to 1. We just saw that. So we would have an arrow that goes from 1 to 8. That's that arrow. But we would also have an arrow that goes from 8 to 1. And so that's why it's a double arrow. Okay. What about 2? Well, the new second place goes to what was in the 6th position, namely 6. Okay, so we have an arrow from 2 to 6, and then we should have an arrow from 6 to 5, which we do, and then we should have an arrow from 5 to 7, which goes up here, and then we need one from 7 to 3, so it jumps way over here, and then an arrow from 3 to 4, which we do, it's a short little arrow, and then we need an arrow from 4, it wraps around to 2. So it starts at 4 and ends at 2. Okay, so this just cycles around. This is a 6 cycle here. So we have every 6 times you perform this shuffle, you reset the packet to its original order. Over here, since this is a transposition or 2 cycle, if you do that shuffle twice, it puts 1 and 8 back in their original positions. Okay, so with the cards that I've just shuffled here, right, we just shuffled it once. So the claim is for the 1 and 8, if we do it one more time, stack right on left, what should happen is we should have 8 and 1 back to where they originally were. Namely, 1 is in the 1st position, 8's in the 8th. Okay, so we have shuffled twice using this shuffle. Now the claim is, because this is a 6 cycle, if we do this just 4 more times, so that's a 3rd time, 4th time, 5th time, and one more, 6th time, what should happen? We should be back to the original ordering of the packet. And we are. We're back to 1 through 8. Okay? Now you can contrast that with the very first shuffle that we did on the far left here. This one resets the packet to its original order after 3 shuffles. So all of the cards get moved back to where they originally started if you perform that shuffle just 3 times. For this shuffle, to achieve that same thing, you actually have to perform that shuffle 6 times. And during those 6 shuffles, the 1 and 8 will be bouncing back and forth between each other, but by the time you perform the 6th shuffle, you'll straighten those out where 1 will be back in the 1st position, 8 will be back in the last position, and all of the other cards will be back to where they originally started. Okay? Now down here, let's take a look at this one quickly. Now because the notation here may not be crystal clear to everyone, I thought we would go ahead and just perform the shuffle at least. Okay, so this is called an RC shuffle. R is for row, C is for column. I use that name because it reminds me that the stay stack principle may very likely apply to that shuffle. Okay, so let me go ahead and interpret what this is. So what you're doing here that's different is you're dealing into 4 piles. Okay, that's different. We were dealing into 2 before. So you deal into 4 piles like so. So we call this pile 1, 2, 3, 4. Okay, so what's being noted here? Well, in mathematics, you do the innermost parentheses first. Well, that would be these 2. So that indicates we should put pile 1 on top of pile 2. Okay, so we've done that. Now we take this and stack it on top of pile 3. And then we take all of that and stack it on top of pile 4. So really all of that can be summarized as just stacking the piles from left to right. Okay, that's a way to mathematically notate stacking the piles from left to right. Well, the claim is that we're going to get a permutation and cycle notation that looks like that. Okay, so let me just show you what we get first, and then we can just point out the details here that I've already written up. Okay, so we got 5, 1, 6, 2, 7, 3, 8, 4. 5, 1, 6, 2, 7, 3, 8, 4. Okay, so this is in the Cauchy two-line notation. That can be pressed down to single line notation, in other words, cycle notation. So 1 goes to 5, 5 goes to 7, 7 goes to 8, 8 goes to 4, 4 goes to 2, and then 2 goes to 1, and then that means we've cycled back around. Okay, so you can write this more succinctly as 1, 5, 7, 8, 4, 2. Okay, so this is a 6 cycle, and so it would take performing this shuffle 6 times for all of these values to be reset to where they originally started. Okay, and then we haven't, this is only 6 of the 8 values, so there's still 2 that we need to account for, and that would be 3. 3 goes to 6, and 6 goes to 3. So this is a little 2 cycle, or in other words, a transposition. Okay, and so those 2 together represent all of what's going on here in this 2-line notation. Okay, and then if we color code it again, what we'll see is it also leads to an inversion, because if we color code 1, 4, 6, 7 is black, 2, 3, 5, 8 is red, we can see that each time you perform this shuffle, cards values of one color get replaced with values of the opposite color. Black 1 goes to red 5 goes to black 7, and so forth. And then here, red 3 gets sent to black 6, and vice versa. So those just switch places every time you form that shuffle. And once again, we get a very different looking shuffle diagram, don't we? Look at this one. It looks like a pair of lungs or something with there's a line in between. Okay, so why don't we just quickly kind of point this out. So 1 goes to 5. So we need an arrow that goes from 1 to 5, which we do. Where does 5 go? It goes to 7. So 5 would go up to 7. And then 7 goes to 8. So just keep climbing up. 8 goes to 4. So 8 drops all the way down here at the bottom. And then 4 goes to 2 up here. And then 2 gets sent back to 1. And that closes out that 6 cycle. And then we've already noted that 3 and 6 just get sent back and forth between each other. Okay? And then I have a note down here that this shuffle is, quote, the inverse of one that's coming up. It's number 9. It's also identical to shuffle 13, which is one that's coming up. Now I thought we would finish with this one over here, partly because it's a special one. This shuffle here is the inverse of this one. Isn't that curious? Well, what does it mean to be the inverse? It means that if you perform this shuffle and then perform this shuffle, you get back to the original order 1 through 8. Well, from the diagram, it would seem to be reasonable, because look, 8 and 1 get sent back and forth between each other. So if we do that twice, yes, it goes back to where it was. And then notice we get the same looking diagram, but the arrows are reversed. So if you want to just picture this, reversing the actions of each of these arrows here. So we have an arrow that goes from 2 to 6, but guess what? We have an arrow that goes from 6 to 2. So why don't we even just show that really quickly here. So those end up being inverses. And by the way, it's not really at all clear looking at those shuffles that they should be inverses. It really, really isn't. Okay, so here's the new one, the last one for today. Okay, so this is a shuffle in which it's similar to the one we just did, but now we're stacking from right to left instead of left to right. That's the only difference. Okay, so if we begin with our ordered packet, 1 through 8, as we've been doing, And then we go ahead and perform this shuffle. Let's go ahead and do it. It involves four piles, right? 4 piles, left, right. Very good. Now instead of stacking left to right, so remember this is pile 1, 2, 3, 4. So it says stack 4 on 3. Very good. Stack those 2 on top of 2, like that. And then that big packet on top of 1. So really we're just stacking from right to left. It's just the opposite stacking. Well, why that would be the inverse of this upper shuffle is not clear at all. I don't think. So the claim then is, see, we have this new ordering, right? I'll just show you that it's 8, 4, 7, 3, 6, 2, 5, 1. Okay, that's correct. So the claim now is that if we perform the shuffle up above, let me just highlight that again up here, this one. Which shuffle was that one? Well, that's just a left-right on which we're stacking right on left. Okay, just going like that. Well, apparently we should get back to the original ordering of the packet. And we do. We get back to 1 through 8. And boy, I don't know how many people would be able to very quickly discern that this shuffling into 2 piles is the inverse to the one where we shuffle into 4 piles. But boy, do these diagrams make clear that they should be inverses, right? I mean, look at the figure. That's a very strange looking figure. That same geometric shape is right down here. The only difference is the reversal of the arrows, okay? And even here, the arrows were reversed. You don't see it, right? So if you reverse this arrow, it goes that way. First, reverse this arrow, goes that way. So the net effect, it looks the same, okay? So this truly is the inverse of that one. How interesting is that? Okay, well, that's enough for today. We're going to be looking at additional Bessey shuffles. And so remember, a Bessey shuffle is simply a shuffle that preserves Bessey sequences. That's our definition, okay? And it ends up that because Bessey sequences are so versatile and so amazingly constructed that they are, quote, invariant under so many of the small packet-sized shuffles that are used today. So it ends up that many shuffles that people use are actually examples of Bessey shuffles. And they're examples of Bessey shuffles because they preserve Bessey sequences. That's what qualifies being a Bessey shuffle. It has to preserve or invert Bessey sequences. So try out this pair on a family member or friends. Start with 8 cards and do this left, right with right on left, and then do into 4 piles, stacking right to left. And take advantage of the fact that once you do that, you know that the packet's been returned to its original order. Isn't that amazing? So if you have a certain packet, say you have 4 aces followed by, why don't we just do it? So if you have a packet in a certain order, so why don't we put it in chased order? It's called clubs, hearts, spades, diamonds, clubs, hearts, spades, diamonds. That's a very classic ordering of the suits. It's called chased order because the CHSD helps you remember C for clubs, H for hearts, S for spades, D for diamonds. So let's say you have the 4 aces followed by the 4 jacks. So by these last 2 diagrams, the ones that we said are inverses of each other, what you could do is you could say, okay, I'm going to mix these cards, and we'll stack right on left because it's the right thing to do, right? That's why we do it. We want to do the right thing in life, don't we? And we'll stack right to left. Do you want to do any more of those? Do you want to do another left, right? Okay. Right on left because it's the right thing to do. And I guess we can follow it up with doing it into 4 so it doesn't feel left out. We'll stack right to left. And once again, it's the right thing to do. Should we do any more of those? And I should point out that you could do 4 of the dealing into 2 piles, and then do 4 of the dealing into 4 piles. And that will still return the packet to its original order. As long as you do each of those shuffles the same number of times, it doesn't matter in what order you do those. Okay? And so anyway, we've done it twice each. And so right here, you could offer the cards to them. Well, what do we know? We know the top card is an ace of clubs, hearts, spades, diamonds, followed by a jack of clubs, hearts, spades, diamonds. So you could just put that out for them to choose a card at random. And so maybe they choose this one. Well, you know it's a jack of clubs. You just set that down. Okay, and as far as they know, you don't know anything. You've just mixed the cards right in front of them. And so you have them look at the card, and then you look deeply into their eyes and try to divine what card they randomly chose. And so you can, kind of make a game of it and say, well, it's a face card, so it's a jack. And I think it's black. It's a club, isn't it? And so you can look at them and try to wait for some kind of smile or some kind of feedback. But you know it's the jack of clubs. Okay, so eventually you can just reveal that it's the jack of clubs and watch their eyes go big, like, how in the world did you know that I randomly chose that? Because they randomly chose it. They truly did. It's just that by the time we perform those shuffles in the way that we did, they undo each other. So it gets back to the original order that we had knowledge of. Okay? So anyway, that's just another simple example of what you can do once you understand permutations. So thank you for watching. In fact, I'll show you what we'll do next time. We'll be looking, oh, look at those. Those are cool ones. We'll be looking at these 4 shuffles and the effect that they have on a packet of 8 cards, and whether they preserve Bessey sequences or invert them, and ways in which you can use your understanding of all of this to design fun and engaging card effects. So thank you for watching.